In this video, we finally get started on what I would consider to be the point of Calculus 1, what Calculus 1 is all about, which is the derivative. The derivative is this quantity that we talked about in video 00, which could be used to measure how fast a function is changing, and which can be used to take a curved object and approximate it by simpler linear objects. Now, as a word of caution, I'm going to spend several days, I think about 3 videos worth of time, talking about what the derivative represents conceptually and about how it can be used. And we're going to spend a lot of time talking about that before we introduce techniques that can be used to actually calculate the derivative quickly. Once again, philosophically, the derivative is something that you often will in real life be calculating via computer. You, the human being, your job is to know when to use that derivative, how to use that derivative correctly, and to know enough about how to calculate the derivatives to be able to detect when the computer might be throwing an error at you and giving you a wrong result. Today we're going to give an informal definition of the derivative as a rate of change. We're going to introduce a very inconvenient formula for the derivative of a function called the difference quotient formula. We're going to talk about the many different ways that the derivative is represented in text, and we're going to talk about derivative and its relationship to some moving object problems, to velocity and acceleration. To set the stage, I want to go back to this recurring example that we have where we have a car that's moving and we are allowed to take 2 snapshots of the number of miles on the car's odometer. Even something like a video is really just a sequence of pictures. Those pictures are taken very close together, but they are individual photos of the car in movement. So we have 2 photos of the car in movement, the car's odometer, at 2 different times. Now, if those pictures of the car's odometer are taken very far apart, for example, if we take one picture at time x equals 1, and we take another picture 2 hours later at x equals 3, and if we use those 2 pictures and the average rate of change formula to get the car's average speed, then that average speed of the car in that 2-hour window is going to in general be a pretty bad estimate of the car's actual speed at the very instant when x was equal to 1. Because during that 2-hour time window, the car had a lot of opportunities to slow down or speed up dramatically. However, if our 2 snapshots begin to get closer and closer together in time, we get a better estimate of the car's actual speed at the instant when x is equal to 1. When the snapshots of the car's odometer get closer and closer together in time, we remove the opportunity for the car to accelerate or decelerate in a dramatic way. So the idea is, I'm going to take an imperfect, a bad, an approximate idea of the car's speed, and I'm going to make that estimate become perfect by taking the average rate of change and moving the right endpoint of the time interval closer and closer and closer to 1. So in other words, I'm going to take the number of miles on the odometer at some later time. Let's call it x2. I'm going to subtract the initial number of miles on the odometer. I'm going to divide that by the difference in the 2 times, and this is the average rate of change. This is the car's average speed. But in order to make that average rate of change into a perfect representation of the car's actual speed at the instant when the time was 1 unit, I'm going to apply a limit. And I'm going to force the right time endpoint, x2, to get closer and closer to the time 1. I'm going to squeeze that time interval and make it smaller and smaller and smaller. And I'm going to do that by using a limit. When we apply this limit to this average rate of change, it's no longer an average. Now this entire quantity is a perfect measure of the car's actual speed at the very instant when x was 1. This is the idea that we will be devoting our time to in this class. This idea of taking an average rate of change and applying a limit to that average rate of change so that it becomes a measure of what's called the instantaneous rate of change. How fast is the function's value changing at one single instant? The instantaneous rate of change of a function f of x at time x equals a is given by a limit as x2 approaches a of f of x2 minus f of a, x2 minus a. Basically, this is the limit of the average rate of change on the interval from a to some secondary right endpoint, some secondary later time. We let that secondary time get closer and closer to the initial time so that the average becomes not an average anymore, but now a measure of instantaneous change. The instantaneous rate of change tells you exactly how fast the function f of x is changing at any given moment, any given instant. No averages, no uncertainty, no ambiguity. The limit eliminates those things. Now, some examples of instantaneous change in real life. If you have a function f of t which measures the position of a moving object at a time t, then the instantaneous rate of change of f of t is a measure of the object's speed. If your function already measures the speed of a moving object, then if you calculate the instantaneous rate of change of velocity, you get what's called the object's acceleration. How fast is the object's speed changing? To what extent is it moving faster or slower? Now, to date, we have done a lot of examples where the input variable is time, because I do think that this is the easiest to conceptualize in cases where the input is time. However, this is not the only situation where the average rate of change formula can be used. For example, you might have a function f of x, which is telling you the amount of money that you will have in 30 years if you invest X dollars right now. For example, here I am on an investment calculator. Suppose that I start out and I invest an initial amount of $20,000. This would represent one particular X value. In 30 years, I would have $114,000 in the investment. That would be the corresponding Y value. If I change that X a little bit, and now I'm investing $30,000, the amount of money that I have after 30 years has changed to $172,000. If I invest $50,000 now, I'll have almost $300,000 later. And if I invest $100,000 now, I'll have almost $600,000 later. So the instantaneous rate of change in this context would be something that measures how adjusting your initial investment affects the amount of money that you have 30 years from now. In this case, the instantaneous rate of change is a measure of how much adjustments to the input value, how much adjustments to the initial investment affect the output value, which is the amount of money that you would have in 30 years. We can also use this in the case where you might have a function that measures the angle of an object that's moving around in a circle. So in this case, the instantaneous rate of change of that function, who is a function of time, would be a measure of how quickly the object is moving around in a circle. Now, this language of instantaneous rate of change is it's a real pain to say it over and over and over again. It's just too long. So we introduced this word, the derivative, as a shorter replacement for that. So when you see the word derivative, you should think of this as being synonymous with the phrase instantaneous rate of change. The derivative is the same thing as the instantaneous rate of change. The derivative is the limit of the average rate of change as the interval gets smaller and smaller and smaller. So if you need to calculate the derivative, you can use the same formula for the derivative that we gave above for the instantaneous rate of change. But the formula that we gave above, I'm going to be honest with you, is not always the most convenient. So I want to introduce an alternative formula, an alternative/additional formula, which can be a little bit easier to use sometimes. The idea is this. Instead of having to carry around like an a and x2 and let x2 approach a, we're going to say, okay, I'm going to take the average rate of change on the interval not from a to x2, but the interval from a to a plus a little something. We're not going to make our interval very big. We're just going to make the right endpoint a little bit larger than the left endpoint. For example, you might have the interval 1 to 1.001, which we could express as 1 plus a little something, 1 plus 0001. In that case, the average rate of change would be plug in the a plus h on the right side to f, plug in a on the left side, subtract those, and then take a plus h and subtract a. The reason why this alternative additional formula is nice is because you can clean up the a plus h minus a in the denominator and get f of a plus h minus f of a divided just by h. So we get a really simple denominator. So having expressed the average rate of change in this format, if we want to get a derivative formula, all we have to do is apply an appropriate limit to this average rate of change so that the time interval gets smaller and smaller and smaller. So what we're going to do is we're going to take this average rate of change formula and we're going to apply a limit. We're going to apply a limit and we're going to let h get closer and closer to 0. When we let h get closer and closer to 0, a plus a little something, a plus h, gets closer and closer to a. by shrinking h, we succeed in shrinking the entire interval. So this is called the difference quotient formula for the derivative. Difference because of the subtraction that is happening in the numerator, quotient because we have a fraction here, difference quotient. And there are a couple of ways to represent this quantity in mathematical notation. The derivative at x equals a is most commonly represented by the letter f, and then a big apostrophe, and then parentheses a. This is the derivative of the function f at a. The instantaneous rate of change of the function at a. Less common, but you'll still see it from time to time. df dx with a vertical bar and then an x equals a. The d here stands for difference, and it comes from the fact that when we take the average rate of change, we're taking a difference between two values of f, and then we're dividing it with a difference between two values of x. The vertical bar with the x equals a is just telling you that you're interested in the rate of change at x equals a, not at any other time or location. So here's an abstract example so that we can practice using the difference quotient formula. Let's let f of x be equal to 3 times x, and let's find the derivative at x equals 1. So in that mathematical notation, we will denote this by f with an apostrophe next to 1 in parentheses. You'll hear this read out loud as f prime of 1. So what I'm going to do is I'm going to set up this formula, the limit as h approaches 0 of the average rate of change f of a plus h minus f of a divided by h. A is the x value that you are interested in your calculations. So a is the number that's plugged in next to f prime. A is 1. A is the given x value. So what am I trying to find? I'm trying to find the limit as h approaches 0 of f of 1 plus h minus f of 1 divided by h. That's what I'm trying to find here. Now, if I'm going to stand any chance of calculating this limit, I want to be able to simplify this as much as I possibly can. So I'm going to work on simplifying this quantity, and I'm going to focus my attention first on trying to figure out what is f of 1 and what is f of 1 plus h. So f of x is 3 times x. If I plug 1 into x's position, I get 3 times 1, which is 3. If I plug 1 plus h into x's position, then I get 3 times 1 plus h, which can be simplified to 3 plus 3h. Now that I've found those individual quantities, I'm going to replace the f of 1 plus h and the f of 1 in my difference quotient formula. So I'm trying to find the limit as h approaches 0 of f of 1 plus h, who was actually 3 plus 3h. much simpler. What was f of 1? F of 1 was 3 divided by h. Now the 3 minus 3 cancels out, and we've got the limit as h approaches 0 of 3h divided by h, and those h's cancel out. So we're left with the limit of just this constant value 3. We're left with 3. So what are we saying? We're saying that if 3x represented the position of an object after x hours had passed, then the object's speed at time 1 would be 3. Let's get a little bit more practice with a slightly more complicated function. Someone says, this time my function is 1 over x. My goal is to find the derivative, is to find the value of f prime at x equals 2. So in this case, I need to use that difference quotient formula with an a value of 2. So I'm going to take the limit as h approaches 0 of the function evaluated at 2 plus little something. Take away f at the initial 2, divided by h. And as usual, in order to stand a chance of simplifying this, I'm going to need to be able to figure out what are these quantities f of 2 plus h and f of 2. So if f with an x in it is 1 over the x, then f with a 2 in it is 1 over 2. And f with a 2 plus h in it would have to be 1 over 2 plus h. So, having made note of that, let's stick that into the difference quotient formula. F of 2 plus h is 1 over 2 plus h minus f of 2 all over h. Okay, so now I need to simplify this creature. Whenever we're taking the limit of a rational function, we need to simplify that rational function. So, when we have a fraction within a fraction, we look at the smaller fractions first, and let's work on simplifying those. To subtract two fractions, they've got to have the same denominator. So let me stick in an extra factor of 2 plus h to the fraction on the right, and an extra factor of 2 to the fraction on the left. Now both of these fractions have exactly the same denominator, so we can combine them. And all of that is all over h. So we're still working on simplifying. And in the numerator, I notice that I have a 2, and then I'm taking away a 2, and I'm taking away h. So if I simplify that subtraction in the numerator, then I get 2 minus 2 is gone, and all that's left is minus h. This is then being divided by h. Now, one of the nice things that happens when you divide fractions is that instead of dividing by a fraction, you can multiply by the reciprocal. So instead of dividing by h, I'll multiply by 1 over h, which gives me two h's that I can cross-cancel. So now I have the limit as h approaches 0 of the fully simplified rational function -1 over 2 times 2 plus h. Once you've fully simplified your rational function, you can find the limit by plugging in the value of h. We have negative 1 over 2 times just 2 now, and we have negative 1 over 4. This is how we would calculate the derivative of 1 over x at the point where x equals 2. So if the original function f of x equals 1 over x represented the position of a moving object, then this quantity would represent the velocity of the moving object at the time 2. Now, you may not be familiar with a situation where an object's velocity can be negative. So what I want to do is I want to take a moment to talk about some physics quantities when it comes to motion and how those quantities are measured. So in all the scenarios that we will be dealing with in this class, we're going to have an object which is moving in a straight line path. For example, an object is moving on a straight road, or an object is falling straight down, something of that nature. Now, when you represent the movement of an object along a straight path, you need to make two decisions. The first thing that you need to decide is what the starting position on this path will be. For example, you might decide at random, I decide that the starting position is right here. You also need a sense of which direction along the line represents quote-unquote forward. So I might arbitrarily decide I'm going to let the right side be the forward direction. So any object that's moving toward the right will be moving quote-unquote forward. When we measure the position of an object, the position is always measured relative to the starting position. So if we say that the position of an object is 0, that means that the object is at the start. Also allow position to take on either positive or negative values, depending on whether the object is in front of or behind the starting position. So for example, if we were measuring the position of an object with the convention that the starting position will be right here and the forward direction would be this way, then an object located back here, say 20 units, or maybe 20 meters to be specific, behind the starting position, this object would have a position of negative 20. Velocity is the technical term for when we are looking at an object's speed, but we are allowing the speed to take on either negative or positive values. The agreement is that the object's velocity will be positive when the object is moving forward. The velocity will be negative, will communicate the fact that the object is moving backward. So for example, if we had an object that was moving backward at a speed of 10 miles per hour, we would say that that's a velocity of minus 10. Acceleration is a measure of how fast velocity is changing. And we'll go more into detail about this in a couple of days, probably about 1 week from now. More on acceleration later. Now, the velocity of an object is the instantaneous rate of change of position. So suppose that we have a function f of x equals x squared representing an object's position at time x. Suppose we wanted to figure out the object's velocity at time x equals 1. What we can do is we can say the velocity is the instantaneous rate of change of position. So if I want the velocity, then I can calculate that by taking the derivative of the position function. So in other words, if I want the velocity at time x equals 1, I can calculate what we called f prime of 1. So let's bust out our difference quotient. We're looking at f of 1 plus a little something minus f of 1 divided by h, where f of x was equal to x squared. If f of x squares x, then f of 1 squares 1. And f of 1 plus h squares 1 plus h. Now while I'm here, let me go ahead and simplify 1 plus h, and let me FOIL it out, as they say. So that would be 1 squared, 2 times 1 times h, plus h squared. So just as a note, what I've just used there is the formula a plus b quantity squared equals a squared plus 2ab plus b squared. So let me stick that data into this difference quotient formula. And we get 1 plus 2h plus h squared. Take away f of 1, which is just 1, divided by h. Let me go ahead and simplify. 1 minus 1 is gone. Let me continue to simplify. If I factor h, 2 plus h over h, then I can get rid of this common factor of h, and now my function is completely simplified, and I can plug in h equals 0. And I get 2 plus 0, which is just 2. So if we have a function which represents the position of an object by x squared, whatever the units might be, then what is the speed of the object at time x equals 1? The speed of the object would be 2 units of speed, whatever those happen to be. That's the kind of thing that the derivative can do. It can allow you to take a position function and get the object's velocity. We'll see many, 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 many more examples of applications of the derivative over the next several days. To summarize what we did, we reviewed the issue of average rate of change, and we discussed how allowing the time interval for average rate of change to shrink causes that average rate to become an instantaneous rate, causes that approximation to become perfect. We gave some different language and notation for the instantaneous rate of change. That phrase is really long, so we just call the quantity derivative, the derivative for short. We gave a formula for the derivative, and we practiced using it. Then we introduced some motion terminology, and we practiced using the derivative to find the velocity of a moving object.